On behalf of my colleague, Dr. Matt Spangler from the University of Nebraska in Lincoln, and me, welcome to this module entitled Beef Genetics Basics. I'm Bob Weber, and I'm a professor at Kansas State University, and I'll be your presenter for today's module. I hold a PhD in animal breeding and genetics from Cornell University and have more than 20 years experience in beef cattle genetic evaluation. I've worked as both an academic and a breed association technical staff member. An overview of today's module focused on beef genetics basics includes a review of the sources of information that we use in genetic prediction for beef cattle, an overview of the basic genetic model, some discussion about the sources of variation that affect phenotypes that we collect in the beef business, and lastly, a review of some genetic concepts, including heritability and genetic correlation. The sources of information that we use in beef cattle genetic improvement in the United States include pedigree information reported by individual breeders as they register calves at a various breed association. In this example, we're using a record from the American Angus Association of an individual bull produced here at Kansas State University. We reported this animal's pedigree, its sire and dam, and birth date information. Later, we reported some individual phenotypic records on the animal, including birth weights, weaning weights, calving ease scores, and a variety of other information. To gain insights into this animal's genetic merit for end product attributes, we collected phenotypic records using ultrasound data. These ultrasound records include percent IMF, or marbling, ribeye area, scan weight, fat depth. In some cases, we actually also report carcass data on harvested animals into our genetic evaluation system. But for animals that are destined to go into a breeding herd, ultrasound provides good indicator trait data. Genetic evaluation systems here in the United States also leverage genomic information. So this animal was genotyped using a high-density genotyping platform to provide some insights into the genetic complement that it inherited from its sire and dam. The current opportunities we have for selection or genetic improvement in beef cattle involve trade-offs, and those trade-offs include the accuracy of selection, or how reliable or useful the data is that we use in our selection decisions, the intensity of selection, or how choosy we are in which animals that we decide to move into the breeding herd, and lastly, generation interval, or how quickly we turn over our populations under selection. At the end of the day, we need to know as much information as we can about as many animals as we can, as quickly as we can. These features speak to the importance of gathering phenotypic information from a wide number of animals, or a broad number of animals in our selection population, completely phenotyping them, or collecting many phenotypic observations across a range of traits. And we also know that time plays an important role, so we need to get information reported into the genetic evaluation system, analyzed, and reported back out as genetic predictors as quickly as possible. As we continue to think about beef genetics basics, our first step is to review the genetic model. So the basic model we use in genetic evaluation in beef cattle, like many other domesticated livestock species, is this: that the phenotype of an individual animal is a function of both the genetics that it inherits from its parents, as well as the environment in which it's reared. So we partition phenotype into genetic and environmental effects. We can further partition, if we choose, the genetic effects into three components: the additive genetic effects, or the things that we use EPDs, or expected progeny differences, to predict or model; the dominance effects, which are the pairing of gene effects; and epistatic effects, or the interactions among genes. At the end of the day, the expected progeny differences that we report reflect a complement of the genetic effects and the interactions amongst genes that an individual animal has. We don't typically model the D and I components separately in our genetic evaluation systems. We focus on additive effects. Our genetic evaluation then uses the phenotypic variation that we observe between animals and partitions that variation to get at genetic effects. The animal-to-animal variation, again, is a source or is caused by variation in both genetics, so the additive, the things that we select for, the non-additive effects, or the heterotic or hybrid vigor. We'll talk more about those in a future module. And also environmental effects, so differences, say, in forage environment, production system and management, and so forth. The effects that we model in our genetic evaluation system include things like the gender of the calf, the age of the calf. We know that older calves typically weigh more than younger calves, and things like age of dam. We know that calves born to younger cows typically weigh less at weaning time than calves of older, more mature cows. So we examine the variation that exists between individual animal phenotypes to help build our models. We exploit the genetic contribution to phenotype in selection. So we've partitioned the environmental component and the genetic component when we have our EPDs that are produced, and we use those EPDs or exploit them in selection. Non-genetic variation can be modeled in our systems. So things like contemporary group, which we'll talk more about in a module on EPD calculations, gender or sex of the calf, age of dam, breed composition, and heterosis effects all influence the phenotypic record of an animal, but with appropriate data reporting can be modeled to correct and make unbiased phenotypic records. Our goal then is to adjust records to equalize animals for non-genetic effects, which cause variation in the phenotype. The idea here is to ensure fair competition. We want to make an apples to apples comparison. So reducing or modeling variation that's associated with known factors enables that fair competition. The objective of our genetic evaluation is to find or predict an animal's genetic merit. And we want to get as close to that animal's true genetic merit as we possibly can with our prediction tools. So consider this example. We have an individual calf that is produced by the mating of these two parents, the sire and the dam. The laws of additive genetics tell us that the average calf born to this mating will have an EPD that lands halfway in between the sire and dam's EPDs. But we know that many calves don't receive the average genetic complement due to random assortment from their sire and dam. As such, we need to inform our genetic predictions using information that we collect in various phenotypes or genomic information to move an animal's EPD from this pedigree estimate to something that's much closer to that animal's true progeny difference. That process enables us to do a better job in selection. We've accounted for the genetic difference, the complement of genetic material, if you will, that this individual animal has inherited from its sire and dam. The difference between an animal's true progeny difference and the estimated pedigree estimate is a thing that we call the Mendelian sampling effect, or Mendelian sampling term. And it's simply a measure of how different is the genetic complement that this individual animal inherited from the average of its sire and dam. In our modern genetic evaluation systems, again, we use phenotypic record and inspections of those phenotypic records and modeling, as well as the genomic information to inform our predictive models. We know that there's a variety of selection tools available for individual producers to use in their selection processes. They include things like DNA markers, expected progeny differences or EPDs, performance ratios for various traits, adjusted records for various traits, raw observations or weaning weights, yearling weights, etc. collected by producers, and visual appraisal. What we know is that as we move up this list, the cost of those individual pieces of information increase. A DNA marker test result costs much more than collecting a weaning weight, for example. But we also know as we move up this list that the pieces of information are better in terms of generating response to selection. They're more precise. They've done a better job of isolating genetic effects away from environmental effects. As such, we should try and focus on attributes that are near the top of this list to use in our selection systems. So some important beef genetics concepts that you should be aware of and will help you in learning modules that may come later include the idea of heritability. So heritability is simply the proportion of variation between individuals that is under genetic control. Again, it's the proportion of phenotypic variation between individuals that is under genetic control. So in this picture, the lighter blue circle represents the entirety of phenotypic variation, say, in a group of animals. And the dark blue circle then represents the portion of that variation that's under genetic control. So again, it's the ratio of additive genetic variance to phenotypic variance. In this case, for a trait like weaning weight, for example, may have a heritability of, say, 40%, which means that 40% of the variation in phenotype is due to genetics. Heritability provides us some measure then of the amount of genetic control a particular trait may be under, and in some cases, what opportunities we may have to make genetic improvement or selection in that individual trait. Maybe more precisely, it's a reflection of how much progress we might make if we were to put a trait under selection. Because some traits, even though they have low heritabilities, are still very economically important. They may respond slower to selection, but that selection is still important from an economic standpoint. So again, for traits to respond to selection, they must have a heritable component. Few traits have heritabilities of 1, but a few do. So if we think about qualitative traits like horn status, either horned or polled, or coat color, genetics describe that variation very precisely. So they may have a heritability that's close to 1. And again, just because a trait has a heritability that's low doesn't mean that that trait's not worth selecting for. So some examples include, say, stability or fertility, economically very important traits in production, but typically have low heritabilities. The environment still plays a large role in those traits. Other examples include disease resistance and calving ease. Lastly here, heritability again quantifies the magnitude that genetics influence a particular trait. Genetic correlations are another concept that's important to understand as we think about genetic evaluation systems. Genetic correlations reflect the relationship, more precisely the linear relationship between two traits. Genetic correlations are caused by pleiotropic genetic effects, or a gene or set of genes that affects 2 or more traits. So think about, as an example, the growth traits. So birth weight, weaning weight, yearling weight, carcass weight, all have strong positive genetic correlations between them, caused by an underlying set of growth genetics. The genetic correlation is a number, ranges between -1 and +1. And the sign and magnitude represent both the strength and directionality of that linear relationship between the two traits. Genetic correlations are a driver of correlated response to selection. So for example, if we make selection on trait A and don't pay any attention to trait B, and trait A is genetically correlated to trait B, then we should expect response or change in trait B when A is under selection. Here's an illustration of a genetic correlation between two traits. This genetic correlation represents a correlation of 0.5 between weaning weight and post-weaning gain. We know on average that animals that tend to have heavier weaning weight genetics have heavier post-weaning gain genetics. So as weaning weight increases, so does post-weaning gain on average. This is caused by an underlying set of genes that affect both traits. Again, the pleiotropic relationship. It's important to note here, since the genetic correlation is not one, that there are some individual genes that affect either weaning weight or post-weaning gain independently. In summary, in this module, we've covered the basic genetic model. So again, phenotype is a function of genetics and environment. Phenotypic records are affected by various effects that cause variation. These include the gender of the calf, age at observation, age of dam, breed, and others. We collect data from multiple sources and use that to inform our genetic predictions in our genetic evaluation systems. Heritability is the proportion of phenotypic variation that is under genetic control. Genetic correlations are the result of pleiotropic genetic effects and the underlying cause for correlated responses to selection. As you consider opportunities for continued learning, please consider completing module number 2, Understanding EPDs. Some related concepts to today's module, or this module, include EPDs in module 2, multiple trait selection in module 5, and utilization of genomic information, which is covered in module 7. For more information on the U.S. Livestock Genetics Export Group, please visit our website at https://www.uslge.org.